Figure skating is one of the most beautiful yet challenging sports in existence. But then again, I may be a little biased. However, figure skating excellently portrays the concepts in physics we have learned over the course of the semester. In the movie Ice Princess, a physicist was able to make it to the top level of competitive figure skating by her knowledge of physics alone. Let's see what she had to say.
The application of physics to the required elements of competitive figure skating. Now, I am going to increase the centripetal force by tucking in my arms. This will increase my moment of inertia, so I will spin faster. I will increase the height of my jump by applying more force to my toe pick.
Though the plot is unrealistic, there is some truth to her claims. First, let's start with the fundamentals of skating on ice. Ice is nearly frictionless. This is why beginners have such a difficult time adjusting to skating at first. There are two types of friction, static and kinetic. Static friction acts parallel to the surface of contact to keep the object from sliding by forming surface adhesion bonds. Kinetic friction acts opposite to the sliding object and still parallel to the surface of contact. In kinetic friction, the surfaces are sliding too much to form these surface adhesion bonds, so the object just slides across the surface unopposed. As frictionless as ice is, there must be some level of friction for figure skating to be possible. The blade on the figure skate is concave, and it must be kept sharp to allow skaters to utilize two edges. The blade cuts into the ice, causing deep edges, which in turn cause static friction. The static friction allows the skater to increase their resistance on the ice and gain speed. Static friction is turned back into kinetic friction when the skater uses force to stop. If the blades are not sharpened, the blades just slide over the surface and the skater will not be able to grip the ice. This lack of grip causes the skater to fall. Generally, skates are sharpened every 6 weeks. So the next time you try ice skating, be sure to grab a sharp pair of skates. It's the principle of momentum that makes figure skating so fun to watch. Skaters thrust themselves into the air by pushing into the ice just before takeoff. This causes the torque needed to propel them in the air to rotate. Of course, the path traveled in the air by the skater is described by projectile motion. The skater rotates about her center of mass. Angular momentum applies to a mass rotating about an axis of rotation, and that's exactly what figure skating is all about. When a skater is spinning with her arms outstretched, her mass is distributed over a greater area. When she pulls in her arms to spin or rotate in the air, she has a smaller moment of inertia and greater angular velocity since momentum is always conserved. While rotating, the skater must keep her center of mass directly in line with her pivot or landing foot. When these are not aligned, the skater loses balance and falls, and of course, there are very painful consequences. What is absolutely crucial to a figure skater's success is her air position. In order to maximize both angular velocity and maximum height, skaters need to be as tight as possible in the air. As seen here by Mireille Nagasu, this is the most ideal air position. Both legs and arms are tight, and the body is completely vertical. The air position seen here by Alyssa Cisney is counterproductive. Her right leg is at nearly a 90-degree angle. This causes her moment of inertia to increase, so upon landing, she will not be balanced and will fall. More proof on the significance of air position is seen here by my triple Salchow. As you can see, I take off into the air, but right around here, my legs are open and my center of mass is not directly over my landing foot. So needless to say, I fall. But now, with my knowledge of physics, I hope to be able to land the more difficult jumps.